general relativity, step by step. Last time I was talking about stupid coordinate systems that behave themselves in one region but did peculiar things in other regions of space-time. That meant that your mathematical description of what happens in some region of space-times is a little bit odd compared to what happens in others. And this oddness might be a gradual leaning over or gradual curve of your coordinate system, or there might actually be a kink in it. There's no unusual physics going on here. It's just that your method of talking about it, your mathematical description of physics in this kinked area here, is a little bit difficult to deal with. But there's no odd physics. And I'm going to show that that's the case in the Schwarzschild geometry. So I'm just going to write it out again. ds squared equals minus 1 minus 2m over r dt squared plus, oh, I'm not going to write that, it drives me nuts, minus 1 over r. My unit of distance is, what was it, 20 kilometers? Which is the Schwarzschild radius, of course, dt squared. Plus dr squared over the same thing, plus r squared d omega squared. Okay, so we've got this system here, that's ds squared, and I'm going to consider r is greater than 1. I'll always do r is greater than 1 first, because, well, we're living in r greater than 1, so it's got to work. So we've got r is greater than 1, implies that we've got minus something positive, dt squared. I'm going to make p for a positive number, strictly positive, because we are strictly greater than 1, plus, well, it's 1 over p, isn't it? dr squared over p, again positive, plus r squared d omega squared. So just looking at the signs of everything, these guys here are the space-like coordinates. This one here, because it's got a negative multiplier, is a time-like one. So that says that t is time-like, as it should be. And what have we got? R, theta, and phi, which are the radius and the angles here for the spherical coordinate system. These are the space-like coordinates because they have positive terms here. Or at least we can make them positive. Right, so that's that. Now what happens if we consider r is less than 1? We've got dt squared times 1 minus 1 over r plus dr squared over the same thing plus r squared d omega squared. These guys here are still space-like because they're multiplied by something positive. If r is less than 1, we have got dt squared times something positive because it's minus something negative, plus dr squared over minus p, so positive, plus these other terms here, r squared d omega squared. So these are still space-like, no problem. However, look what's happened here. This one here is now the time-like coordinate, because the metric tensor has got a negative coefficient. This one here is space-like. So it's a bit like what happened here, not the king, but when the coordinate system bent over what was a timeline. You could follow this line as a world line, because you can follow this coordinate line here until you get to here, in which case you need to move faster than light, and that's not possible. So what's happened here is that the identity of the coordinate system in terms of space-like and time-like coordinates has been altered by these this line turning over. And we've got the same here. What we've got here is, for r is less than 1, t is a space-like coordinate, and r is time-like. And so what that means physically is that r changes in much the same way that outside the event horizon, outside r equals 1, the time coordinate, t, marches forward because time goes forward, because it's a time-like coordinate. inside the event horizon, r is the time-like coordinate. And so if time goes forward, your r changes, and we'll see later that r decreases with proper time. And so we have a very peculiar, well, it's not a peculiar system. We've chosen a peculiar coordinate system to describe perfectly normal, sensible physics. But something's gone wrong at r equals 1, or something very complicated has happened at r equals 1, because the time-like and space-like nature of your coordinates r and t have swapped roles. And we'll come back to that next time. Stop.